Hello everyone, welcome to the Material Science class MIC 300. This is the second video of chapter 7. In this chapter we are discussing the dislocations and the strengthening mechanisms. Over the previous chapter or video, we discussed the plastic deformation and how it could be related to the dislocation motion. And we said that in order to achieve plastic deformation inside the material microstructure, there should be a dislocation, that it should be moved. And we described the motion of the dislocation by two things. Like there should be slip plane, and we define the slip plane. This is the plane over which the crystallographic plane over which along which the dislocation line is going to move. In addition, the dislocation line is going to move in a certain direction. So the slip plane and the direction of motion, this defines something that we call a slip system, and this is what we are going to discuss over this video or over the first part of this video. So we have discussed the plastic deformation, and we discussed in detail how the edge dislocation is going to move and how these dislocations could be related to the bonding, the type of bonding between the atoms of that form the material, and how it would be easy for us for a dislocation or for a dislocation to move inside the material structure, or even how it would be easy for us to achieve a plastic deformation depending on the bonding between, or the type of bond between the atoms. This has been discussed over the previous video. In the meanwhile, we discussed what does it mean dislocation density. We discussed the lattice distortion or the lattice strain that is going to be produced because of the existence of an edge dislocation or even a screw dislocation, and even we discussed the interaction between these different dislocations. This is what have been covered over the previous video. So we're gonna start here by discussing something that we call a slip system. As I mentioned, in order to fully describe the dislocation motion, and remember that the dislocation motion, this is the thing that indicates that there is a plastic deformation in the material. So to describe this dislocation motion, this requires two things. Require a slip plane and a slip direction. So what does it mean, a slip plane? The slip plane, this is the crystallographic plane along which the dislocation line is moving or is going to move, as we explained over the previous video. We said that for a dislocation to move, the dislocation line or the dislocation is going to move over a certain plane of atoms. This plane of atom is known as the slip plane. So this is one thing. In order to describe the motion of a dislocation, you should identify the slip plane over which this dislocation, edge dislocation or screw dislocation is going to take place, or motion is going to take place. Also, we have in the meanwhile to describe the slip direction. So what is a slip direction? This is the direction of the dislocation line movement. As we discussed here over the previous video, we said that the dislocation moves following a certain direction. So this direction, it should be a direction, crystallographic direction within the material microstructure, depending on the crystal structure of the material. In the meanwhile, there should be slip plane, which is this plane over which the dislocation is going to move. So these two things, the slip plane and the slip direction, these what define the movement and the type of the plastic deformation that is going to take place inside the material microstructure, depending on what? Depending on the crystal structure. So the slip system, it is the combination of the slip plane and the slip direction. So in order to describe how the dislocation is going to move, this requires a slip system. This slip system, it is a combination of a slip plane and a slip direction. It means that you have to define the slip plane and the slip direction that describe the plane over which the dislocation line is going to move, and the slip direction, which is the direction of the line dislocation movement associated or related to the dislocation motion. The slip system depends on the crystal structure. How? There is a condition in order to identify this slip system, because if we're going to look to any crystal structure, and this is what we have covered over chapter 3, that any crystal has so many different crystallographic planes and has so many different crystallographic directions. This is what we have covered, and we practice how we can identify these crystallographic planes and crystallographic directions over chapter 3. So the question is, over which one of these crystallographic plane the slip is going to take place, or the dislocation line is going to move? The second issue, following any direction, because we have so many crystallographic directions inside one specific crystal structure. So following any one of these directions, so many directions that this dislocation is going to move. So the slip direction and the slip plane, it is one specific plane and one specific direction or it could be multiple planes or multiple directions that belong to a specific crystal structure that identify how the dislocation is going to move inside the material microstructure, indicating that there is a plastic deformation. So there is a condition that makes, or based on which we can identify the plane, the slip plane and the slip direction, or we can identify the slip system. So the slip system is chosen, or it is determined such that the atomic distortion that combine the motion of the dislocation, it should be minimum. This is the condition. Why? Because any material has a resistance to the plastic deformation. It is not that easy that we can achieve a plastic deformation for any material. The material resists the dislocation motion. There is a dislocation that it should be moved in order to achieve a plastic deformation. So it is not that easy to achieve the dislocation movement. All the time the material tries to minimize or eliminate the dislocation movement, because as we discussed, as there is a dislocation movement, there is a lattice distortion, there is atomic distortion that is going to take place. And this is something weird to the material, unusual to the material, and the material try to minimize the atomic distortion or the lattice distortion because of the dislocation movement. And for the material to achieve this, to minimize the atomic distortion, it will allow the dislocation to take place over a specific plane and following a specific direction known as the slip system. So the slip system is chosen such that the atomic distortion that combines the dislocation motion is minimum. This depends on two requirements that we have to achieve. First thing, that the slip plane, remember the slip system requires that you define slip plane and slip direction. So the slip plane, how we can identify the slip plane? The slip plane, this is the plane that has the most dense atomic backing. As we discussed in chapter 3, we may have different crystallographic planes, and these different crystallographic planes, they are different in terms of something that we call as planar density. And we practiced in chapter 3 how we can calculate the planar density for any material, right? So what is the planar density? It depends on the number of atoms distributed over a specific crystallographic plane of the crystal divided by the area of this plane. So this planar density describes how dense this plane will be filled with atoms. So the atomic backing, it should be dense. Dense, it means that we should have more atoms over this plane. So the crystal structure or the material allows the dislocation to move over the plane with the largest number of atoms, or the most dense atomic backing plane. This is known as the most dense atomic backing plane. This plane is the plane with the largest or the greatest planar density within the crystal structure. We discussed, for example, I'm just going to refresh your mind with these things. In chapter 3, we discussed the calculation of the planar density. Even there was an example that we knew how we can calculate the planar density for two different planes inside the material microstructure. We calculated the planar density for a plane which is 100, which should be one face of an FCC crystal structure, for example. So if we have done the calculation for the planar density for this surface or this plane, we're gonna get it by 15.3. Then when we calculated the planar density, but for another plane which is 111 plane, we got it 17.67. So as you can see, if we try to compare the planar density of the plane 111 to the plane 100, we're gonna find the planar density of the plane 111, it is bigger. This means that this plane 111, it is more dense. It has a dense or more or bigger density in terms of the atomic backing. It means that the slip plane is most likely to be 111 plane, not 100 plane. You got my point? So within this FCC crystal structure, there are lots of planes. There are so many different planes that we can identify, but which one of all of these different planes that we can say that this is the plane with the greatest or the greatest atomic backing and the largest or the greatest planar density, and in that case this plane is going to be counted as the slip plane, that it should be over which the dislocation line is going to move. This requires that you should investigate the planar densities of all of these different planes and identify the largest planar density, and this plane with this largest planar density, this definitely is going to give you the slip plane. So this is the first condition. How we can identify the slip plane? It is the plane, the crystallographic plane of the so many crystallographic planes within a specific crystal structure that describe what had the most dense atomic backing, and this is the one with the largest planar density. How about the slip direction? It's gonna be the same. The slip direction, it is from the definition, from the title, since we are talking about the direction, so we are talking definitely about the linear density. Also, we practiced in chapter 3 how we can calculate the linear density for different crystallographic directions. So the planar density, it is related to the crystallographic planes, but the slip direction or the linear density, it is related to crystallographic planes. I mean direction, and in that case, so we can say that the slip direction corresponds to the direction in this plane. So it is a one direction. So there is a condition that you have to identify the slip plane first. And within any crystallographic plane, and this is what we discussed in chapter 3, it can have infinite number of directions. Any plane, you can draw infinite number of lines in different directions. You're going to end up with so many infinite number of these crystallographic directions. So within any specific plane, there are lots of crystallographic direction. We have to choose some specific one or more specific crystallographic direction to be the slip direction. This slip direction, it should belong to the same slip plane that you choose in step 1. So it is a direction in this plane. I mean in the slip plane. So you have to choose the slip plane. Once you located this slip plane, which is the one with the bigger planar density, this plane has so many crystallographic directions. You're gonna choose some specific directions or only one direction. It depends on the plane and it depends on the crystal structure that will be counted or considered as the slip direction. So the slip direction, first, there is a condition that it should be direction within the slip plane that you choose in step 1. Make sense? So the slip direction corresponds to the direction in this plane that is most closely packed with the atoms. What does it mean? It means that you have to choose the same, either like the slip plane, you have to choose the slip direction. This is the direction that is filled with atom, that is more dense with atom. This one is the one with the largest or the highest linear density with the so many crystallographic directions of the slip plane that you choose. So this is how we can identify the slip system for any crystal structure or for any material, depending on what? Depending on its crystal structure. And this what defines the slip system. So again, the slip system, it is the slip plane and the slip direction. What is the benefit or the thing of the slip system? We are using it to describe how the dislocation is going to move inside the material structure depending on the crystal structure of the material. This dislocation motion, this is what indicates that there is a plastic deformation, and the slip system should be described by slip plane and slip direction. The slip plane, this is the plane that with the largest planar density. It could be only one plane or multiple plane. You may have, depending on the crystal structure, you may have a crystal structure that has only one plane that it could be counted as a slip plane. Why? Because this is the largest plane with the largest planar density. But in some other crystal structures, you may have more than one plane having the same largest planar density. So in that case, all of these planes would be counted or considered as slip plane. The same thing, the slip direction. Within one specific slip plane, you may have only one direction with the largest linear density, or you may have more than one direction having the same largest linear density. So in that case, you're gonna collect all of them, all of these directions as slip directions for this crystallographic plane or slip plane. So this is how we can define the slip system of the material, and again, this depends on the crystal structure. So let us discuss the slip system, a slip plane and slip direction for the three different crystal structures that we have covered over chapter 3. In chapter 3, we discussed the FCC crystal structure, and we said that this is the thing that has a cubic shape, and there should be an atom that located at every corner, and there should be an atom located at the center of every face. And also we're gonna see what is the slip system in the BCC crystal structure, and also we're gonna discuss this for the HCP crystal structure. So let us start with the FCC crystal structure, face-centered cubic-centered face-centered cubic crystal structure. So the slip system in any material with FCC crystal structure, it will be described by these two things. So what is this 111 that is confined between this special bracket? This indicates a plane, a family of plane. If you recall in chapter 3. So that's why it is recommended, before you watch this video, you go over chapter 3 first. Especially to understand how you can define a crystallographic plane, how you can define a crystallographic direction, how you can define a family of plane. So for example, as we discussed in chapter 3, the 111 family, this is a family of equivalent crystallographic planes. So all of these planes are equivalent plane, and we define the equivalent crystallographic planes are parallel planes having the same, having identical indices, especially if we're gonna talk about the cubic crystal. So in a cubic crystal, and you, in case that you have multiple planes, and these planes are parallel, so they will be counted as equivalent crystallographic planes, and we can combine all of these planes to one family. This family can be represented in that way, using any three indices of any one of these parallel planes. So this is a family of planes. All of these planes are parallel within the specific crystal structure. For example, but this symbol, this thing indicate like 110. This is a family of crystallographic directions, not crystallographic plane. So it is a family of equivalent crystallographic directions, and we define that the equivalent crystallographic direction, these any two directions to be equivalent, they should have with different indices. They gonna be with different indices, but the spacing between the atoms along each direction will be the same. Or in other words, the length of every one of these directions should be the same to be counted as equivalent crystallographic direction. So again, if you have two different directions with two different indices, are they equivalent or not? This requires a condition. What is this condition? If you calculate the length of the first direction and the length of the second direction, and both they're gonna give the same length, so they are equivalent. This length indicating that the spacing between the atoms along this direction is going to be the same, and this what identify you to have an equivalent crystallographic direction. In case that you don't have a cubic crystal, as we discussed in chapter 3, the directions having the same indices with no regard to their order or their sign, they are equivalent direction. For example, in case that you have a crystallographic direction that 1, 2, 3, it is equivalent to 1, 3, 2, or also equivalent to 1, 3, negative 2. So with no regard to the sign, whatever there is a sign or difference in the sign, difference in the order, we don't care, since they do have the same indices 1, 2, and 3, so they are two equivalent crystallographic directions in a cubic crystal. This is only for cubic crystal like FCC crystal structure or BCC crystal structure. So coming back again to this thing here, the slip system, and this is something that you should understand, for any material with FCC crystal structure, its slip system, it is 111 and 110 as a family of crystallographic plane and another family of the crystallographic direction. Make sense? So this is what defines the slip system for any material with FCC crystal structure. What does it mean, this slip system? It means that the dislocation, in case that this material is going to be plastically deformed, the dislocation of this material is going to take place over, the dislocation is going to move over a crystallographic plane. This plane should belong to this family of crystallographic planes, and it's going to follow a direction. This direction should one of the directions that belong to this family. So this indicates that the slip system, it is not only one single plane or one single direction. No, it could be a family of planes, it could be a family of directions, because as I said, all of these directions, all of these planes, they are the ones with the largest planar density and largest linear density, as we define the conditions for identifying the slip system for any crystal structure. So for the FCC crystal structure, it is not just only one plane that could be considered as a slip plane. No, it is a group of planes, lots of planes that belong to this family. 111. Like for example, the crystallographic plane 111, it is one of the planes that belong to this family of planes. The same thing, the direction 110, it is one of the directions that belong to this family. So any plane that belong to this family, it could be considered as a slip plane. Any direction that belong to this the direction family will be considered as a slip direction. This is what defines the slip system for a crystal structure or a material with FCC crystal structure. Why? How did we know that this is 111 or 110? Because in FCC crystal structure, the 11 plane family, this is the one with the highest and the largest atomic backing. This is the one with the highest or the largest planar density. Any plane that belong to this family, this is the highest planar density ever for any FCC crystal structure. Also, the 110 direction family is the one with the directions belong to these planes, direction that belong to the 111 family of planes with the highest linear density. So this is what defines, this is why the slip system in the FCC crystal structure has been identified by this family of planes and this family of direction. Why? Because these are the two that the planes, these are the planes with the largest planar density. The direction, these are the direction that belong to this family of plane with the largest and highest linear density. So for example, a typical example of this plane is the slip plane is going to be one of the planes like 111 that belong to this family. Example of this plane is the one, as a plane it should be parentheses. So the plane 111 plane. So this is an example, one of the planes that belong to this family, which is already represented here for FCC crystal structure. So this plane within the FCC crystal structure, this is the one with the largest planar density. If you try to calculate the planar density of this plane and compare it to any other plane within the crystal structure, definitely this is going to be the largest planar density ever for FCC crystal structure. The same thing, if we're going to choose this plane, how many directions that we can draw belong to this plane? We can draw infinite number of directions. If you draw any line at any direction, this is going to give a crystallographic direction that belong to this plane. For example, if you connected this point to this point, this is going to give you a plane, a direction, a crystallographic direction. So this is a direction. If you connected this point to this point, this is going to give you another crystallographic direction. Here we're going to have another crystallographic direction. So all of these are so many crystallographic directions. The question is, which one or ones of the crystallographic direction that belong to this plane that will be considered with the largest linear density? If we have done calculation to all of these so many infinite number of crystallographic directions, we're gonna find that there is three directions having the same largest linear density. These directions are the direction that belong to this edge, that to draw a direction, whatever, going down or up, that belong to this edge, another direction that belong to this edge, whatever it goes right or left, and another direction that belong to this edge, whatever it goes up or down. So these, if you calculated the linear density for this line over this direction, the linear density over this direction or this direction, you're gonna find that the linear densities for the three is equal, is the same, and this is the largest linear density for any other direction that is belong to this plane, 111 plane. Make sense? So the plane, this is what defines the slip plane, and the direction is going to be any one of these three directions that belong to this family, which is 110, that family. For example, this direction, it is 110. Like for example, you're gonna go to 1. If you started from here, you're gonna from this is the 0 point, so you're gonna go 1 in the x direction and 1 in the y direction. So this, 111 is gonna be this direction. This direction, it is 110 direction, right? This direction is gonna be 101 direction. This direction is gonna be the 0, 1, 1 direction. All of these three directions are equivalent. Why equivalent? Because this is a cubic crystal, and no matter what the sign or the order of the indices, they having the same indices as 0 and double 1. 2 ones and 1 0. So it is these, all of these crystallographic direction, they are equivalent and they belong to the same family. Whatever you name the family as 110, or even you can name the family as 101. Also you can name the family as 011. All of these are representing the same family of the same crystallographic directions. So this is what defines the slip direction. So the question is, what is the number of the slip system? What does it mean, the number of the slip system? What are the possibilities? Because as I said, the slip plane, it is not just one plane, it is different planes. And the slip direction, it is three directions. It is any direction that belong to this family, that belong to this crystallographic plane. So there are different scenarios, there are possibilities, there are lots of options here. So if you counted all the combinations between the slip plane and the slip direction, all the possible slip planes and all the possible slip direction that belong to this family and this family, you're gonna end up with 12 combinations of plane and direction, and this gives you 12 possibilities of the slip system for any FCC crystal structure. Why? This requires that you explain or investigate how many planes that belong to this family, how many directions that belong to this family. And if you did the multiplication, you're going to end up with the 12 possibilities of 12 options, and this is what we are going to explain. Make sense? So the number of the slip systems is 12 in the FCC crystal. Why? Because this depends on the number of the plane that belong to this group or family of crystallographic plane. In addition, it depends on the number of the directions that belong to this family of the directions. So for example, if we're going to consider the 111 plane family, this includes 4 different and unique and independent planes. And these planes, even in the FCC crystal structure, can be represented as shown in these 4 representations. So this family contains 4 planes. These planes are, one of them is the plane 111 plane, crystallographic plane that is connected between this point and this point at this corner, at this point at the other corner. Also, we can turn this plane the other way around, like instead of connecting this point, we can connect this point to the same 2 points. So connecting this point to the same 2 points here, this is going to give you another plane, but the indices of this plane will be 1, -1, 1. So as you can see, these 2 planes, they are still belong to the same family. Why? Because they do have the same indices as already shown here, and they are representing 2 equivalent planes, or crystallographic plane that could be located within the same family. The same thing, this crystallographic plane, if you connect this point to these 2 other points, this is going to give you the -1, 1, 1 plane. This is another crystallographic plane that still belong to the same family of this crystallographic plane 1, 1, 1. And if you connect it, instead of connecting this point, you can connect this other point. So this is going to give you another option. So there are 4 different planes that still belong to the same family. So these 4 planes, they are belong to the same family as 111 plane. So these are 4 options. Within every one of these single planes or 4 planes, there are 3 possibilities of the crystallographic directions. Any one of these directions would be counted as slip direction. So we do have 3 different directions. There is one direction over this plane, and another direction, and another direction. As we discussed here, this plane has 3 directions. Any one of them could be considered as a slip direction. Why? Because all of them, they do have the same largest linear density. So the same thing here. This plane has 3 directions, and this plane has also 3 directions, and this plane has 3 other directions, and this one has 3 other directions. So if you counted how many possibilities for every plane, there are 3 directions. So every plane represents 3 possibilities of a slip system. If you choose the plane with this direction, this gives, if you choose this plane with this direction, this is going to give you slip 1, the slip system number 1. And the slip system number 2 is going to be the same plane but with this direction. The slip system number 3 is the same plane but with the third direction. So this gives 3 slip systems. The same thing, this one is going to give another 3 slip system. This is going to give another 3 slip system, another 3 slip system. So if you counted 4 times 3, this gives 12 slip system, and that's why the number of the slip systems in the FCC crystal structure it is 12. So why? Because there are 4 unique planes that belong to this family of the plane 111 family, and within each one of these planes there are 3 independent directions that belong to the family 110 family of crystallographic plane. So for example, the first slip system, you're going to have the crystallographic plane, which is this one 111, and the slip direction, the direction will be 1, -10, and the same plane, you still have the same plane. So all of these 3 slip systems, they do have the same crystallographic plane but different directions. So this is direction 1, direction 2, direction 3. The same thing. This is another 3 of groups. There is -1, 1, 1, 1 plane, -1. There is -1, and 3 different directions. And then you're going to have another 3, which 1, -1, 1, 1, 2, 3, and 3 directions. And there is 1, -1, 1, -1. This is going to give you another 3 with the other 3 directions, crystallographic directions. So this gives in total 12 options, 12 possibilities that the dislocation line is going to move or following any one of these 12 slip systems. Any one of them is going to follow any one of them. It depends on the direction of the applied force. It depends on the type of the material itself. It depends on so many other things. But anyway, if there is a plastic deformation that is going to take place to any FCC crystal structure, or any FCC material with an FCC, in any metal with FCC crystal structure, depending on the applied shear stress, depending on the applied force, and depending on other things, the dislocation is going to move following any one of these 12 slip system. It's going to follow only one. Which one? We don't know. As I mentioned, this depends on the applied load direction and other things. Make sense? So how about the BCC crystal structure? How about if we have a metal with BCC crystal structure, how many slip systems? In the BCC crystal structure, it is not only one option like the FCC. In the FCC, we do have only slip system type, which is 11 and 110 as crystallographic planes and direction, and this gives 12 options or 12 possibilities of this slip system. So it is only one slip system type that is found for FCC crystal structure, but for BCC crystal structure, we do have 3 slip systems, 3 types of the slip systems. In one slip system that you're going to have the crystallographic plane will belong to one of these families, like either 110, this gives a slip system. There is another slip system that belongs to the family 211, and the crystallographic plane, there is a third slip system which is 321. So in the FCC crystal structure, we would have only one slip system with 12 possibilities, which will be 12 slip systems that belong to one type of the slip system. But here we do have 3 types of the slip system. We do have a slip system that uses a crystallographic plane 110, another slip system which is 211, another slip system which is 321. Make sense? And in all of these slip systems, the direction, the crystallographic, the same. The crystallographic direction is the same. So within this plane, we do have different crystallographic directions, infinite number of crystallographic direction. Which ones with the largest linear density? Any direction that belong to this crystallographic direction family, which is 111. The same thing here, the same. Any direction that belong to this family is gonna be the one with the largest linear density, and this is gonna define the slip direction. The same thing, for the 321 crystallographic plane, the direction that belongs to this family is the one that is gonna define the direction of the slip direction. Make sense? So if we're gonna count how many, the number of the slip system that belong to these 3 options, as I mentioned, this depends on the applied load, depends on the material type. So probably in case that you have a metal with BCC crystal structure, there are three types of this slip system. We have type 1 that has a crystallographic plane 110 and the direction 111. Type 2, the crystallographic plane will be 211 and the direction it is 111. For the type 3, it is 321 and the direction it is 111. All of these three planes, they do have the same planar density, which is the largest planar density. So these are different possibilities, and the choice of any one of these possibilities basically depends on the material type. For example, like alpha iron or molybdenum and the tungsten and the brass. All of these different types of material, their slip system will belong to this family of the crystallographic plane 110 and this family of the crystallographic direction as 111. But for example, the molybdenum and the iron and the tungsten and the sodium, so these will belong to another family of material that their slip system will typically gonna follow the 211 crystallographic plane and the direction will be 111 direction. The same thing, the iron and the potassium will follow the 321 crystallographic plane and the crystallographic directions or the slip direction will be 111 direction. So this is another slip system that could be used for these types of materials. So the number of the slip systems, for example, for this option or this scenario or this possibility of the slip system, it is 12. Why 12? Because you're going to have like 4 crystallographic planes that as unique planes that belong to this family. It's going to be 6 crystallographic planes that belong to this family of 110. And every one of these planes has 2 independent directions. Every one of these planes has 2 independent directions. So if you multiply it 6 times 2, these 2 independent directions that belong to this family 111, it will be 1 direction in this one and 1 direction over the diagonal over this rectangular plane. So this gives you 2 directions. Multiply times 6, this gives you in total 12. But for the 211 direction, you're gonna have 6 possibilities or 12 possibilities of this plane with the same planar density. Like for example, if you connected this point to this point and the mid of these 2 sides, this is gonna give you a plane. But if you switch, for example, these 2 points in the middle with the mid of these 2 edges, this is gonna give you another plane. So it means that if you're gonna try the other options for this plane, you're gonna end up with 12 plane, and every one of this plane has only 1 direction with the largest linear density, which it should be through the main diagonal of this plane. So this is gonna give you 1 times 12 options of the crystallographic plane. This gives you in total 12 possibilities of the slip system. So the number of the slip system with this option will be 12, but the number of the slip system for this case, it will be 24. Why? Because there are 24 possibilities or unique crystallographic plane that belong to this family. Because if you try this family, as we explained in chapter 3, you're gonna end up with 24 crystallographic planes that belong to this family. But this family has 12 crystallographic planes, but this family has 6 crystallographic planes. But since you have 6 crystallographic planes and 2 directions, this gives you 12. Here you'd have 6 crystallographic planes, but only 1 direction, so this gives 12. Here you'd have 24 crystallographic plane that belong to this family with 1 direction for each plane. This is going to give you 24 as the number of the slip system for a BCC crystal structure or a material that belong to this or following this slip system option. Make sense? So this is, for example, why the number of the slip systems for a BCC crystal structure that belong to this slip system as 110111 is 12. Why it is 12? Because we do have 6 unique crystallographic planes that belong to this family. These crystallographic planes are represented as shown here. We do have this plane that is directed in this direction, and this is the opposite direction to it. And we do have this plane that goes over the diagonal in the middle, and this is the opposite direction to it. And we do have another plane, and this is its opposite direction. So as you can see, we do have in total 6 crystallographic planes that belong to this family, and every plane has 2 independent directions. Every plane has 2 directions. Both these 2 directions, they do have the same largest linear density that belong to this plane. So in that case, for every one we're going to have 2 times 6. This gives in total 12 crystallographic, 12 slip system as the number of the slip system for this BCC crystal structure. So this table gives you a summary about the different slip systems and the number of the slip system that belong for a BCC crystal structure, for a FCC crystal structure, or a hexagonal crystal structure, hexagonal closed back crystal structures even. For example, for FCC crystal, we have only one option, one slip system, which is 1, 1, 1 and 1, negative 1, 0, or 1, 1, 0, any direction that belong to this family. And this direction that here we do have, as we mentioned in the FCC crystal structure, every one of these planes, we do have 4 planes, and every one of these planes has 3 directions. So if you multiply 3 times 4, this gives you 12 as a number of the slip system. But in the BCC crystal structure, we do have 3 scenarios, 3 options. We do have the 1, 1, 0, 1, negative 1, 1, 1, or 1, 1, 1. This direction is going to be the same, and 2, 1, 1, and 3, 2, 1. This one has 24 planes. This one has 12 planes, but this one has only 6 planes. But within this 6 planes, there are 2 directions. So that's why we're going to end up with 12 as the number of the slip system. Here we have only 1 direction. Here we have only 1 direction. The same thing. So you're going to end up with the 12 and the 24 for this for these different types of the materials that belong to the BCC or have a BCC crystal structure. The same thing for hexagonal closed back material like HCP crystal structure. So these are the crystallographic planes or the slip planes, and these are the crystallographic directions. And the number, and this is an interesting thing to observe, that the number of the crystallographic direction, the number of the slip systems, in the hexagonal closed back, it is very small in comparison to the FCC or even the BCC crystal structure. There is a reason behind this. This is what we are going to explain. But the number of the slip system for this option, it is only 3 slip system, and here we have only 3, and there we do have 6 slip systems. So as you can see, the hexagonal closed back has a lower number of the slip system. What does it mean this? This means that in case that we do have a material with a hexagonal closed back or a hexagonal crystal structure, the achieving the plastic deformation within this material, it will be difficult in comparison to any material with a BCC crystal structure or even FCC crystal structure. So again, in case that there is a material with a hexagonal crystal structure, the achievement of or the attainment of plastic deformation because of the movement of the dislocation or achieving a movement of the dislocation, it is not that easy. It is why? Because the possibilities that this material can offer as a slip system are limited. We have only 3 up to 6 for hexagonal crystal structures. But it would be much more easy for BCC crystal structure or FCC crystal structure to achieve plastic deformation or to move the dislocations inside the material structure. Why? Because we have so many options of the slip system, so it would be easy for the dislocation to move following any one of these 12 or 24 slip systems. So that's why the plastic deformation or plastically deforming the FCC crystal structure or BCC crystal structure, it is much more simple and easy than doing a plastic deformation to a hexagonal crystal structure. Make sense? So the question now, metals with FCC crystal structure or BCC crystal structure are quite ductile, while the metals with HCP crystal structure or materials with HCP crystal structure, they are quite brittle. Why? What we knew about metals in general, that they are ductile material. Why? Because of their metallic bond and because of the delocalization, as we explained in chapter 2, right? But away from the metal in comparison to the ceramic material, which is a brittle material, even metals, they could have the ductility of the metal material could depend on the crystal structure. We may have a metal with FCC crystal structure, we may have a metal material with BCC crystal structure, we may have another metal material with HCP crystal structure. So all of them are metals. All of them, they should be counted like a ductile material when compared to the ceramic material, for example. But within the material, the metal themselves, Some of the metals, they could be considered very ductile. Some of the other metals in comparison to these very ductile material could be considered like brittle material, like quite brittle. They could have some ductility, but it is not that much like in comparison to these very ductile metals. Make sense? So for example, aluminum, copper, these are very ductile materials. But there are some other metals, their ductility in comparison to the ductility of aluminum or copper, it is very negligible. So this material could be considered like brittle in comparison to these very ductile materials. So the question is, this material with very high ductility, in many of the cases, they're going to be either having an FCC crystal structure or a BCC crystal structure. So a material with FCC or BCC crystal structure, it is most likely to be very ductile material like aluminum and copper. These copper have a BCC crystal structure and aluminum have FCC crystal structure. So why? Because they have a relative number, a very high number of slip system. At least they do have 12 according to this table. In the FCC crystal structure, BCC crystal structure, the minimum number of slip system is 12. This indicates that the plastic deformation of the material is much more easy in this crystal structure or in these materials with this crystal structure. And if you recall in chapter 6, we defined the ductility, that it is a measure of the ability of the material to plastically deform without fraction, the ability of the material to deform with no fraction. So if in case that this material can in case that it is easy to achieve a plastic deformation by the movement of the dislocation inside the material microstructure, this gives an indication that this material is more ductile material. And the reason is that we do have here so many crystallographic number. The number of the the number of the slip system, it is bigger than the hexagonal. This indicates that this material with FCC crystal structure or BCC crystal structure, they are likely to be more ductile than material with HCP crystal structure. Why? Because of the few slip system in the HCP and the large number of the slip system, which at least 12 in the FCC or BCC crystal structure, which make them can be severely plastically deformed. Plastically along the various slip systems, so it would be easy to achieve plastic deformation for a BCC or FCC crystal structure. So this is the reason. So why the FCC, BCC, they are quite ductile in comparison to the HCP? Because of the number, the high number of the slip system, which is at least 12 in the FCC and BCC crystal structure, making it easy for them to achieve plastic deformation without fracture, indicating a high ductility. But the opposite is going to be the same for the HCP crystal structure. Make sense? So after we discussed the plastic deformation and how it could be achieved at the microstructure level, or what indicates that there is a plastic deformation from the microstructure inspections, that there should be a dislocation motion, and we discussed the different slip systems. Now let us discuss the plastic deformation, and let's see how it's gonna take place or is gonna happen in the single crystal material or a polycrystalline material. These polycrystalline material or single crystal material, we defined what does it mean a polycrystalline material over the previous chapters. We said that a polycrystalline material, this is the one that has multiple grains, and every one of these grains represent a crystal. So before we understand how the plastic deformation or polycrystalline materials, how they are plastically deformed and how the dislocation is going to move inside the material microstructure of a polycrystalline material, let us understand first how the plastic deformation is achieved or is taking place in a single crystal material. So let us discuss this part first. The plastic deformation or slip, as we define that the plastic deformation is the slip that describe the dislocation movement over a certain crystallographic plane following a certain crystallographic direction within the crystal structure. So think of it like you have a single crystal, and this crystal could be FCC crystal, BCC crystal, hexagonal crystal, or any other type of the crystal system that we covered in chapter 3. So if in case that you have only one single crystal, and this crystal is subjected to an applied force, like this force F, which is a tensile force, like what we have done in the tensile test in chapter 6. So there should be a plastic deformation that is going to take place in case that this force is big enough to bring the material to the plastic zone or to the plastic behavior. So in that case, this plastic deformation, it will involve a dislocation movement, and this dislocation is going to move following a certain slip system, as we just discussed. So consider the single crystal shown in the figure. The crystal is subjected to an applied stress. This is what we knew from chapter 6, that the stress is force divided by the cross-sectional area of this crystal. So assume that we have prepared a sample of this crystal, and this sample is cylindrical with a cross-sectional area A0. So this is the original area of the cross-section. This is the cross-sectional area of the cylinder. If you divided the force by the cross-sectional area, you're going to end up with the applied stress, which is a tensile stress in that case. If this applied stress is higher than the yield strength of the material, definitely the material is going to exhibit some plastic deformation. And as we said, the plastic deformation, this indicates a slip. This indicates a dislocation motion. It means that a slip will occur. The crystal slip or the plastic deformation is going to take place such that the two planes of atoms glide over one another, or the other option that one plane is going to glide. So what is the difference between sliding and gliding? Sliding, that it means that you're going to have a plane of atom, like this is one plane of atom, and you're going to have another plane of atom in that case, and one is going to move for the right in the right direction, and the other one is going to move in the left direction. So this is sliding, that one moves or the slide with respect to the other one. Or even you probably may have one plane, one of these two planes is fixed, the other one is moving. So this is known as plane of atom is sliding, or this plane of atom is sliding. But what does it mean glides? Glides, it means that like you're gonna have like a delamination, like you're gonna have like one plane of atom and another plane and third plane. Like for example, this plane is fixed and this plane is fixed, is not moving, while the plane in the middle is going to slide with respect to the other one. So this is known as a plane of atoms gliding. It means that it's going to glide or is going to slide with respect to two other planes. So it is kind of delamination that is going to take place between these atoms. Anyway, as long as there is plastic deformation, there should be a movement of these atoms of the planes. These planes, they're gonna slide towards each other or over one another, or even you can have one plane that is going to glide with respect to the other plane. The atom sliding or gliding, this such that they already slide or glide in such a way that a dislocation moves following a specific slip system, as we discussed, and this slip system is defined by slip plane and slip direction. As shown here in the figure, for example, if we applied a stress and this stress is big enough, bigger than the yield strength of the material, there should be plastic deformation, so there should be dislocation movement. The dislocation, for example, is going to slide, or the dislocation line is going to move over this plane. So this plane, it will be considered as the slip plane. This is the slip plane. And it's going to move in this direction. So this is the direction of the sliding or the motion of the dislocation line. So the dislocation line is going to move because of the high force that acting or stress that is bigger than the yield strength to bring the material to the plastic deformation. This dislocation line is going to move following this direction over this slip plane. And the slip direction and the slip plane, these are the two things that define the slip system for this single crystal material. This is what we knew so far over the discussion of this part of the chapter 7, right? So if the applied stress is oriented, as you can see, the applied stress is oriented with respect to the normal, to the slip plane by an angle phi. This angle phi from mathematics, this is the slip plane again, this is the slip plane. From mathematics, any plane to describe or to define any plane, the best way is to define the plane by its normal. What is the normal? This is the normal axis, or the axis that is perpendicular or normal to any surface or to any plane. Like in this slip plane, what distinguishes this slip plane from any other plane within this crystal is its normal. How we can name this plane, we can name it or define this plane by its normal. So if we measure the angle between the normal to the slip plane and the direction of the applied stress or the direction of the applied force, this is going to give us an angle. This angle is known as phi. So let us call or give a name to this angle as phi. So what is the angle phi? This is the angle between the normal to the slip plane and the direction of the applied force or the applied stress. Also, there is another angle between that we are going to define between the direction of the applied force and the direction of the slip. The slip direction. This is the slip direction. This is the direction that the dislocation line is going to follow, sliding over or moving over this slip plane. So if we measure the angle between the slip direction and the direction of the applied force, this is going to give us another angle. Let us give it a name as lambda. So the lambda, this is another angle that is set up between the applied force and the direction or the slip direction. But the angle between the normal to the slip plane and the force, this is going to give us the angle phi. If it is not all the applied stress that will be used for moving the dislocation, but only a component of this applied stress that will be used, known as the resolved or the decomposed shear stress. So as you can see, this stress, this force will produce a normal stress. This force will produce sigma. This sigma is known as a normal stress. The stresses in general, and I'm pretty sure that the mechanical engineers should have an idea about this thing from the mechanics of material class. We do have two different types, only two types of stresses. We do have either a normal stress, which basically we refer to it as sigma. This is in case that the material is stretched or compressed. A typical example of this normal stress, that the stress that comes from a tension or compression against the material sample. But there is another type of stress which is known as a shear stress. The thing that is needed to move a dislocation is a shear stress. It is not a normal stress. The normal stress doesn't move a dislocation inside the material. This requires a shear stress, and this shear stress, it should be parallel to the slip plane. It should be parallel to the slip plane. And when you from physics, when you from mechanics of material, that the stress that is parallel to any plane, it will be considered as a shear stress. But the stress that is normal to the plane, it is a normal stress. You got it? So that's why in order to achieve plastic deformation or in order to move the dislocation inside the material structure, this requires a shear stress that is parallel to the slip plane. This external stress, it is normal. This applied stress, which is external, acting over the entire material, it is a normal stress. But it's going to be decomposed because of the inclination of this slip plane. This slip plane, it is not perpendicular or normal to the direction of the applied stress. It is oriented with respect to the applied stress with these two angles, alpha and gamma. So in that case, this means that there should be an orientation, and this stress can be decomposed into two components or even three components if we are working in 3 dimensions. Some of these components will be shear stresses. These shear stress, these are the things that are responsible for moving the dislocation inside the material microstructure. This means that not all the applied stress, it is not all the applied stress that is going to move the dislocation, but part of it, a component of the applied stress, is the thing that will be used for moving the dislocation inside the material microstructure. But how about the other component is going to do other things? But the dislocation is going to move with a component, a part of the applied stress. This part is known as the resolved shear stress or the decomposed shear stress. Okay, like one component of the shear stress. So what is the resolved shear stress? It is a component. It is a part of the applied stress that is obtained by resolving the applied stress with the normal to the slip plane and the slip direction. We are going to do decomposition to these forces along two different directions, along the normal to the plane direction and the slip direction. This is going to give us the component of the stress, the component, the part of the applied stress that is needed to move the dislocation is known as tau. Tau, this refers to a shear stress R, which indicates resolved. So this is the resolved shear stress that is needed to move the dislocation, equals sigma, which is the applied stress. How we can calculate this applied stress? Simply divide the force that acting over the sample divided by the cross-sectional area of this sample, which is this normal cross-sectional area. You're gonna end up with sigma. If you plug it here, you're gonna calculate the tau R, the resolved shear stress, how much it is. It is equal sigma times cosine phi cosine lambda. This requires that you're gonna do some transformation over the different axes till you're gonna end up with this expression for the resolved shear stress. Make sense? So this is the amount of stress needed to achieve the or move the dislocation inside the crystal structure. Any single crystal has in general a number of slip systems. As we discussed, for example, the FCC crystal structure has 12 slip systems. The BCC crystal structure has either 12 number of slip system or 24 number of slip system, depending on the material type. The same thing for HCP. So depending, here we are talking about a single crystal. The single crystal is subjected to a force. So there is a dislocation that is going to move as long as this force is bigger than the yield strength of the material. But the question is, the dislocation motion is going to follow which one of these slip systems? If for example, if this crystal is FCC crystal structure, there are 12 slip systems. There are 12 possibilities, or there are 12 directions and ways by which the dislocation is going to move inside the crystal structure. But as I mentioned before, this depends on the direction and the type of the applied stress, the applied force acting over this material. So basically, these slip systems have different angles, phi and lambda. Angles with respect to the applied stress. Phi, this is the angle between the normal of the slip plane and the applied force, and the gamma, this is the angle between the slip direction and the applied force. So we do have like 12 possibilities. So for every single slip system, there is a phi and there is a lambda value. There is a specific value for the angle phi and the angle lambda with respect to the applied force. So thus each slip system will have its own resolved shear stress. So for example, you have 12 slip systems. Your objective is just to calculate the angle phi and lambda for the first slip system that have this a specific crystallographic plane and crystallographic direction that describe the slip plane and the slip direction. Once you calculate phi and lambda, you're gonna plug it into this expression to calculate the resolved shear stress. Then you're gonna repeat again for the second slip system. You're gonna find alpha, phi, and lambda. Then you're gonna repeat the calculation for the resolved shear stress till you finish the 12. So you're gonna end up with 12 different values for the 12 slip systems of the resolved shear stress. So the question is, the dislocation is going to move following which specific one of this slip system is gonna follow the one with the maximum value of the resolved shear stress. So this is how we can calculate, or we can judge which one of these slip systems the dislocation is going to follow, is going to move over which slip plane, over which slip direction. This depends on the direction of the applied force with respect to the slip plane and the slip direction of these 12 slip systems. If you're gonna calculate these angles and calculate the resolved shear stress, the slip system with the largest or the greatest or the biggest resolved shear stress, this is the slip system that the dislocation is going to follow and move following this dislocation system. So the slip system that activates, this is known as a slip system activation, because we do have 12 slip system. Which one is going to activate? To activate, it means that the dislocation will move following this slip system. And the one with the maximum resolved shear stress, so the maximum resolved shear stress is the one that gives the angle theta, that makes an angle phi, an angle lambda, that gives the resolved shear stress maximum. The yield strength of the crystal can be then defined with respect to the activated slip system using this expression. So for example, if we decided to approximate the calculation for the yield strength Why the yield strength? Because before the yield strength, there is no movement of the dislocation. The dislocation will start to move upon we subject the material with a stress that is bigger than, or at least it should equal to, the yield strength of the material to move the dislocation. So the yield strength, it can be calculated as tau critical shear stress. This CRSS, the first CR stands for critical, SS stands for shear stress. So this is a critical value of the shear stress that is needed to move the dislocation inside the material microstructure, divided by the maximum resolved shear stress that depend on the slip system. Like you're gonna choose which slip system that is gonna give you the maximum resolved shear stress. You're gonna plug it here in the denominator, and if you're gonna use the critical shear stress value, which it should be a material property, so the critical resolved shear stress value, it is a material property. It depends on the material type. It is specified for every single crystal and depends on the material type that represent the minimum. It represents the minimum shear stress that is required to initiate the slip. To initiate the plastic deformation, we said that plastic deformation means slip. To initiate the slip, it means to initiate the plastic deformation. This is the minimum value of the shear stress required to initiate the movement of the dislocation inside the material microstructure. Following a specific slip system, if you divided this critical value by the maximum resolved shear stress for this crystal, depending on its slip system, you're gonna end up with an approximate value of the yield strength of this material, how much it is. Make sense? So this is simply how the plastic deformation is done within a single crystal material, and this requires, as I mentioned, a specific value for the shear stress, and this applied stress, it should be bigger than the yield strength of the material to achieve this plastic deformation. And it is not all the applied stress, it is part of it that it will be used for moving the dislocation. This part is known as the resolved shear stress. Also, we knew how we can determine the yield strength in case that we have an idea about the resolved shear stress that it requires to initiate the slippage of, or the motion of the dislocation inside the material microstructure in case that we are dealing with a single crystal. So these things describe the plastic deformation in single crystal material. Make sense? So let us consider this example on the resolved shear stress and the stress to initiate yielding computation. Like let us consider that you do have a single crystal of BCC iron. So the material, it is iron, and the iron, it has a BCC crystal structure that is oriented such that a tensile stress is applied along the direction 0, 1, 0 direction. So you do have a sample like a single crystal. This single crystal, it is iron. We don't care so much about the material type as much as we care about the crystal structure type. It is BCC crystal structure. And this crystal structure, it is subjected to a tensile stress. It is tensile stress, tension stress that is acting on the direction 0, 1, 0 direction. There are two requirements, and the first requirement is to calculate the resolved shear stress along the 1, 1, 0 plane and in the negative 1, 1 direction when a tensile stress of 52 megapascal, which is equivalent to 7,500 psi, is applied. So as we discussed before, in the BCC crystal structure, we have three scenarios, three possibilities of the slip system. One of the slip system is the 1, 1, 0 and the 1, 1, 1 or the negative 1, 1 direction. So this is the slip plane and this is the slip direction that already specified for this material. So it is required to calculate the resolved shear stress over this slip system. So any slip system, it is defined by a slip plane and slip direction. So this is the slip plane and this is the slip direction. And the direction of the applied stress, it is 0, 1, 0 direction. So let us finish point A, then we're gonna move next to point B. So to solve this thing, first you have to imagine or to draw the BCC crystal structure You're just gonna draw a cube in this way. So the BCC crystal structure has a cubic form. There should be some atoms distributed, like there should be one atom at every corner and there should be one atom in the middle. We don't care about the distribution of the atoms as much as we care about these directions and these crystallographic planes. So first, you're gonna identify the slip system over this cubic system or over this BCC crystal structure. The slip system, the slip plane, it is 1, 1, 0 crystallographic plane. If you recall from chapter 3 how we can draw the plane which is 1, 1, 0 plane. To draw this plane, if you recall from chapter 3, we have to identify the reciprocals for these numbers. So the reciprocal for the 1 will be 1, the reciprocal for the 1 will be 1, and the reciprocal for the other one, the second one, will be 1, and the reciprocal for the 0 will be infinity. It means that the intercept with the plane of the plane with the x-axis, it should be at 1, and the plane should be intersecting with the y-axis at 1, and it should be intersecting with the z-axis at infinity. It means that it should be parallel to the z-axis. So if you decided to draw this plane, the one point of intersection will be at x, because this is like x, this is y, and this is x direction, and this is the z direction. So definitely one point will be the intersection at 1, and is going to intersect with the y at 1, but it will be parallel to z. So a plane, we said, as we discussed in chapter 3, if you just connect these 2 points together, this is gonna give you one edge in the plane. Then since it is parallel to z, it means that you're just gonna draw a line that is parallel to z, another line here that is parallel to z, and then you're gonna close the shape. This is gonna give you the plane, which is shown here, highlighted here in the figure. So this definitely, this is gonna give us, this is the plane, which it should be the 1, 1, 0 plane. This is the slip plane. Any slip plane has a normal. So once you identify the slip plane, let us identify next the slip direction. So what is the slip direction? The slip direction here is identified as -1, 1, 1. So -1, 1, 1, let us start from example from any point, because the slip direction, it should belong to the slip plane. It should be a direction that belongs to this plane. It means that you're gonna choose one of the 4 corners of this rectangular plane, and then you're gonna start to generate the direction or draw the slip direction. So let us start from this corner, for example. You can start from any other corner. And the direction, it is -1, 1, 1. So what does it mean? It means that you're gonna move in the negative x direction 1 distance, 1 equal 1a. So you're gonna move -1. So you're gonna move up to this point. Then you're gonna move parallel to y, 1. Then you're gonna move parallel to z, 1, till you're gonna end up with this point. So you're gonna move 1 in the x negative, another one in the y positive, another one in the z positive. This is gonna give you the end point. If you connected these 2 points together, this is gonna give you the direction. This direction is gonna be the slip direction. This is the slip direction. Make sense? So we identified the slip plane and we identified the slip direction. So this is the slip plane. This is the slip plane. So this is the first thing, that you have to identify the slip system as plane and direction, and this is what we have done. Also, you're gonna identify the direction or draw or indicate the direction of the tensile stress, the applied stress. It is oriented in 0, 1, 0 direction. So the direction of this applied stress, it is 0, 1, 0 direction. Where you can draw the direction of the applied stress anywhere, it's up to you. You can even take it like from the middle of this plane, or you can draw any direction, it's up to you. For example, let us identify the direction of the applied stress from the midpoint of this plane. From the middle of this plane, because there should be like a core atom here. And the direction, it should be the direction of the applied stress. It is 0, 1, 0 direction. Right? So what does it mean? It means that starting from this point, you're gonna move 0 parallel to x, but you're gonna move 1 parallel to y, and 0 parallel to Z. So this is going to give you an arrow or a direction that is parallel to the y-axis. So this is going to give you the direction of the applied stress, which we're going to give it a symbol as sigma because it is a tensile stress as he mentioned. How much is the value of this applied stress? He gave it to us by 52 megapascal. So the value of the applied stress, it is 52 megapascal. This is the value of the applied stress. So the first step is to identify or draw the slip plane and the slip direction, identify the direction of the applied stress. Then your objective is just to identify exactly what are the directions of the applied stress. So the direction of the applied stress, as it is already given to us, it is 0, 1, 0. This is for the applied stress. Then you're going to identify the direction of the slip direction as already given by negative 1, 1, 1. This is the direction of the slip direction. Also, you're going to identify the direction of the normal to the slip plane. Where is the normal to the slip plane? The normal to the slip plane, it should be directed this way. This is the direction of the normal to the slip plane. It should be perpendicular, projected out of the slip plane. So this is the normal. This is the normal to slip plane. Here you are required to identify the indices of this direction. This is a crystallographic direction in this crystal. So what are the indices of this direction? If you decided to draw this direction somehow a parallel, because this one it should be in the middle of the cubic crystal, this is going to be typically parallel to another vector or another direction which can be drawn on the base surface of this BCC crystal structure. So if I ask you, and this is what we knew from the chapter 3, what should be this direction? What are the indices of this direction? If you're starting from this point, you're going to move one parallel to X, another one parallel to Y, but you're going to move nothing parallel to Z. Right? It means that the indices of the normal to the slip plane, it is 1 parallel to X, 1 parallel to Y, 0 parallel to Z. So now we identify 3 main directions that we need them. We need the direction of the applied stress, which was already given to us by 0, 1, 0. We need the direction of the normal to the slip plane, and this is the thing that we just calculated as 1, 1, 0. Also the direction of the slip direction that was given to us by negative 1, 1. So these are the 3 directions that we're going to use them. So the slip direction, we got it by negative 1, 1, 1. Actually it was given. And the applied stress direction, applied stress direction, it was given to us by 0, 1, 0. But the thing that we calculated is the normal to slip plane direction, which we got it by 1, 1, 0. Make sense? Now your objective is just to calculate the angles between these 3 different directions. How we can calculate the angle between any 2 different directions? For example, if we assume this direction, because the indices, as we discussed in chapter 3, we can define them as U, V, W. For example, this index, it could be like U, this is V, and this is W. And this should be U, V, W, since we are working as a cubic crystal. So for example, to find the angle between the slip direction and the angle and the applied stress, this angle is going to be the lambda angle, as we explained here. The angle between the slip direction and the applied stress, it should be lambda angle. But the angle between the applied stress and the normal to the slip plane, this is the phi angle. So that's why we had to identify these directions first to calculate the angle between them, in such a way that the angle between the slip direction and the applied stress, this gives lambda, but the angle between the applied stress and the normal to the slip plane, this gives the angle phi. Once you calculate these 2 angles, you can directly plug into this expression to calculate the resolved stress, where he already gave us this sigma by 52. So this is, and this is going to give us the first requirement. It is required to calculate the resolved shear stress, the tau r, how much it is. In case that the sigma, it is 52, so we need to calculate first phi and lambda, and this is what we are doing. Make sense? So the question is how we calculate the calculate the angle between any two directions. We can simply use this expression. Like assume that you do have two directions. One direction is U1 V1 W1. The second direction is U2 V2 W2. So the angle between them is gonna be U1 U2 plus V1 V2 plus W1 W2 divided by the square root of U1 square V plus V1 square plus W1 square times U2 square plus V2 square plus W2 square. So U1 V1 W1, these are the three indices of the first vector, any one of the two. And U2, V2, W2 will be the other three indices of the other vector. If you plug these indices into this expression, you're going to end up with the angle directly. Make sense? So for example, as we mentioned, the angle phi should be the angle between the applied stress, which has this direction, which has these three indices, and the normal to the slip plane, which has this direction, has these three indices. So let us assume, for example, this is like U1 V1 W1, and this is going to be like U2 V2 W2, and plug this data into this expression to end up with phi. So the angle between the slip plane, or the normal to the slip plane, and the applied stress direction, this angle phi will equal to, according to this expression, the cosine inverse of U1, which is 0, times U2, which is 1, plus V1 V2, V1 it is 1, times V2 it is 1, plus W1 which is 0, times W2 which is 0, divided by, this is on the top, on the denominator you're going to find the square root of U1 square, which is 0 square, plus V1 square, which is 1 square, plus W1 square, which is 0 square, all multiplied times the U2 square, which is 1 square, plus the V2 square, which is 1 square, plus 0 square, which is W2 square. If you have done the calculations, you should end up with phi. You're going to find it by the 45 degrees. If you're going to use the calculator, you're going to find the angle between the normal to the slip plane and the applied stress direction. This is phi. You're going to find it by 45 degrees. Repeat the same for the other two directions. The slip direction and the applied. All the time the applied shear stress is common between the two angles. So you're gonna consider this is like U1 V1 W1, and this is gonna be like U2 V2 W2 when you calculate lambda. So if we have done the calculation lambda, in that case it's gonna be the cosine inverse of, we do have here U1 V1 W1, so it is 0, times the other one here, it is -1, so it is times -1, plus the V1 V2, V1 it is 1, V2 it is 1, so it will be 1 times 1, plus 0 times 1, this is W1 W2, divided by the square root of the U1 is already 0 square, plus 1 square, plus 0 square. So this is going to give us 0 plus 1 plus 0. It should be squared. And all of this should be multiplied times the -1, 1, 1. So it's going to be like the -1 square plus 1 square plus 1 square. If you have done the calculations using the calculator, you're going to end up with lambda will be, the angle will be 54.7 degrees. Once you find these two angles, simply you're going to plug into this expression that the resolved shear stress will be sigma times the cosine of the angle phi times the cosine of the angle lambda that you just got. So simply sigma was given to us by 52 megapascal, so it is 52, and there is no need to do any unit conversions here, just leave it with the same unit as it was given. The angle has no unit, it's just degree. So the cosine angle 45, phi is 45, so it will be the cosine of 45 degrees times the cosine of the 54.7 degrees. If you're going to do the calculations, you're going to end up with the resolved shear stress by 21.3 megapascal, 21.3 megapascal. This is for the resolved shear stress. As you can see, it is lower. smaller than lower than the 52 megapascal. So it means that this crystal, it is subjected to a normal stress with 52. It is not all of the stress that is used for achieving plastic deformation or moving the dislocation inside the material structure, only part of it, only 21.3 megapascal that will be used physically to move the dislocation inside the material microstructure. Make sense? So this is for part A. How about part B? It is required if the slip is going to take place over the slip plane, the same slip plane that we defined before, 110, and over the direction -11 direction. The question is it necessary that this slip is going to take place over this plane and direction or this slip system? No. We said that for the BCC crystal structure, we do have 12 numbers of slip system. We have 12 slip system. It is not necessary that the dislocation is going to move following this specific slip system 110 and -111. It could follow any other one of the 12 slip systems in the BCC crystal structure. But let us assume that it's going to follow this slip system 110 and -111 direction. So what should be, and in case that the critical resolved shear stress. What is the critical resolved shear stress? This is the critical resolved shear stress, which is tau critical shear stress. So this tau critical SS was given by 30 megapascal. So in case that this critical, which is a material property known for the material type for this iron, was given by 30 megapascal, and the dislocation is going to follow this slip system that we just calculated its resolved shear stress, what should be the magnitude of the applied tensile stress necessarily or required to initiate the yielding, which indicate that the stress that initiate the yield, this is the yield strength of the material, how much it is. To calculate the yield strength of the material, we have to use this expression of the critical shear stress divided by the resolved shear stress, which it should be maximum. But here we didn't calculate except only one resolved shear stress. As we mentioned here, to identify this maximum resolved shear stress, you have to do the calculation for the 12 slip systems. But we didn't do this here. We have done it for only one slip system. So he assumed in the requirement B, in point B, he said that the slip system is gonna take place over the 110 plane and the -11 direction. Indicates that assume that this slip system is the one that is gonna give the maximum resolved shear stress. So it means that you're going to use the resolved shear stress that you just calculated in point A, and you're going to plug it into this expression, into this equation, in order to calculate the yield strength. And this is what we're going to do. So the yield strength will be equal to the critical shear stress divided by, as you can see in this expression, it should be divided by the term excluding the sigma, excluding the normal stress. So it should be the cosine of the phi angle, cosine lambda angle maximum. It means that you're going to choose the two angles that is going to give you the maximum resolved shear stress only. So this term, this denominator can be written in another form. We can write this term as the maximum resolved shear stress divided by the applied stress, right? Because if you're going to compare this term to this term, simply you're going to just divide by sigma, both sides. So if you divided the resolved maximum shear stress by the applied stress, you're going to end up with the denominator that it should be used with the tau critical to calculate the yield strength of the material, and this is what we're going to do. So this simply is going to be the resolved shear stress maximum divided by the sigma, which is the normal stress. This is to calculate the yield strength. So equals the critical shear stress was given to us by 30 megapascal divided by how much is this tau r maximum. He assumed, he said, assume that the maximum resolved shear stress is going to take following this slip system. So this means that the resolved shear stress that we calculated in point A, this is point A, this shear stress, this resolved shear stress will be used as the maximum shear stress. So it will be like the 21.3, then you're going to divide by the 52, which is the applied stress. This number is the thing that it should be located in the denominator. The other option that you can plug the cosine of the 54, I mean that you can substitute this term, excluding the 52, into the denominator, you're going to end up with the same value. So it's up to you. If you have done the calculations, you're going to end up with 53.4 megapascal. It means that the yield strength of this material, this means that the yield strength of this material is going to take place at a stress level higher to initiate the yielding. This require an applied stress equals to 73.4. I'm sorry, 73.4 megapascal. So what does it mean this? It means that in order to achieve plastic deformation for this material, for this BCC iron, this requires an applied stress that it should be bigger or at least equals to 73.4 megapascal. So also what does it mean? It means that the 52 megapascal that we're already applying over this material, this will not produce. This will not produce a shear plastic deformation of the material, or even it will not be big enough to move the dislocation inside the material microstructure. But why did we calculate the resolved shear stress? This resolved shear stress, this is just the stress that is going to act or affect over the dislocation line, but it is not necessary to be able to move it. So currently under the 52 stress, applied stress, the shear stress that is going to act over the dislocation inside the material microstructure, it will be equivalent to 21.3 megapascal, and it is not big enough to move it. It is lower than the 30 megapascal that is required to move the material. To move the dislocation inside the material microstructure. So this means that under the 52 megapascal, this material will not yield. The material will not achieve the yield, and the material is still in its elastic zone, and there is no plastic deformation for this material at this stress level. Make sense? So that's it for today or this video. The objective is just to discuss the slip system and understand how we can use this slip system to describe the plastic deformation in a single crystal. Over the next lectures or the next video, we are going to discuss the slip or the plastic deformation in polycrystalline materials, and also we are going to discuss with details the different strengthening mechanism that could be achieved for a polycrystalline material. Make sense? So that's it for this part, and thank you so much for watching, and see you in another video.